In this session, I want to talk about the concept of power, so stay with me. Up to this point, we've talked about concepts like current and voltage, and now we want to discuss the so-called third piece of our puzzle in electronics, which is power. Regarding the electrical current, to briefly recap and reiterate, we previously said that an electrical current is essentially an organized directed movement of numerous electric charges, specifically electrons, that continuously flow through a conductive material or a conductor. And voltage is the driving force that pushes these electric charges to create an electric current. Now, power, which we refer to as tavan, and denote with the capital letter P in equations. If I want to give a simple definition of power, I can say that power is the work done by an electrical circuit. We know what electric current is, but this flow of electrons by itself isn't really that useful to us. Well, in the end, something needs to be done with it. We can only say that this electric current is useful when the energy carried by the current is converted into other forms of energy like heat, light, sound, radio waves, and so on, so that we can have an output. Now, to make this easier to understand, I'll give you a concrete example. Imagine an incandescent bulb. In an incandescent bulb, voltage causes current to pass through the filament inside the bulb. The electrical energy carried by this flowing electric current is then clearly displayed to us as both heat and light. What exactly does that truly mean? It fundamentally means that the very same powerful force that drives those tiny electrons to move and flow, that is a form of energy. Now that energy is converted into heat and light, which is why we see the bulb light up. We can say that this is a practical example of the benefit of having an electric current, and that's why we can say that when electric current is converted into other forms like heat and light, it becomes useful for us. Now, what is a watt, which I wrote here? We talked about electric current and voltage, and we said that each of them has its own unit of measurement. Electrical power is precisely measured in specific units called watts, which we commonly abbreviate with a prominent capital W. So the electrical power that is represented by a capital P in scientific equations has a specific unit of measurement called the watt, and this particular unit of watt is denoted by a capital W. Now, if I want to give a simple definition of a watt, I can say that 1 watt is the amount of work done by a circuit in which 1 ampere of current is conducted with 1 volt. If you pay attention, this itself indicates an equation. So I'll repeat this definition one more time. 1 watt is the amount of work done by a circuit. So we've said that watt is the unit for measuring power, and we've said that power is represented by P in equations, like this. So precisely 1 watt is the amount of electrical work done by a circuit where effectively 1 ampere of electrical current is conducted by precisely 1 volt of electrical potential difference. That is to say, I have exactly 1 ampere of electrical current, which, as we previously mentioned, is typically represented by the capital letter I, that is effectively conducted by precisely 1 volt. Volt is the unit of voltage, and if you remember, we said that voltage is represented by the letter E. So now, this has effectively become a fundamental equation that we can readily utilize here in our calculations, and its more elegant or nicer and indeed more commonly presented form is clearly shown as P equals E times I, which in the vast majority of textbooks and academic resources is typically written with a prominent capital V, which also universally stands for volt, representing electrical potential difference. They typically use the capital letter V to represent the unit of electrical volt or the electrical voltage here, so they commonly write it as P equals V times I in this particular form. Now, they don't put the multiplication sign in between, meaning they just write it like this. I've shown both forms, so wherever you see them, you can use either one. But in physics textbooks, E is more commonly used as the symbol for energy, so I thought it was necessary to also show V here so that if you see such an equation, you know it's the same thing and you just need to substitute the numbers. So, in other words, we can definitively say that this electrical power is precisely equal to the applied voltage, which was our measured voltage, multiplied by the flowing electrical current. Now, in order to use the equation correctly, we need to make sure that we measure power, voltage, and current using their standard units. What does that mean? It means, what did we say is the unit for power? It's the watt. And what did we say is the unit for voltage? It's the volt, and for current, it's the ampere. So in equations, if we're given different units, we need to convert them to these standard units before plugging them into the equation. For example, suppose we have a lamp that's connected to a 10-volt power supply. Now, this power supply could be a battery. Let's assume I have a 10-volt power supply here. Look, here I have 10 volts, and I'll write the unit next to it as well. 10 volts. We have a 10-volt power supply, and there's a current of 1/10 of an ampere passing through the lamp. See, we said 1/10 of an ampere. So here I represent 1/10 of an ampere like this. I'll also write its unit next to it. And now if I want to calculate the wattage for this, it would be like this. This multiplication sign is between them. Now after this, it's just a simple equation. That is, if I multiply 10 by 1/10, I get 1, and the unit is watt. So I write it like this. Now it's better if I show the one like this. So this is also a simple equation that you've learned here, along with how to calculate it. Just be careful, for example, if it says milliampere here, you need to convert this milliampere to ampere, which involves some calculations that I'll explain to you in the relevant sessions. Just know this much for now. This was a simple problem where we said we have a lamp connected to a 10-volt power supply. That is, this is 10 volts and a current of 1/10 of an ampere is passing through it. Now we wanted to calculate its wattage, which is done like this. So in general, we can say that our lamp operates at 1 watt. Why do we say it operates at 1 watt? Because here we had the definition that 1 watt is the amount of work done, the amount of work performed. So here we say that the lamp is operating at 1 watt. Now this equation has other applications as well. For example, like this. Now look, here instead of I put V so you can get familiar with two of its forms. This is actually the same as P equals VI. And now if you have a basic familiarity with math, if I want to find I, here the known is divided by the unknown. And it is shown like this. That is, if I multiply these two together, we get back to the same P. Now consider this as a general equation for now. And again, I emphasize that here instead of E, I have used V. That is, this is the same E, so you should get familiar with both forms. Now, what is its application? Most of the time, we have the voltage and wattage of the circuit, and we want to know how much current is flowing through it. That is, we have the voltage. We also have the wattage, but we don't know how much current is passing through. In this way, we can use this equation to find the amount of current. For example, we have a lamp that is 100 watts. I put 100 here. Now I equals 100. We have 100 watts. Now it's not necessary to write the units. I'm just writing it this way so it becomes more familiar to you and sticks in your mind. We have a single standard 100 watts of power. Our lamp is also precisely 100 watts. Now when we carefully plug it into the electrical power outlet, for example, a significant 220 volts of electricity passes through it, providing the necessary energy. Now we need to do the calculation and see what the current is like. That is, we divide 100 by 220 volts. Now this voltage could be anything else. For example, it could be 100 or it could be 117. It doesn't make a difference. So when we divide these two numbers, we get a result, and I'll write down its approximate value. 0.45, and I absolutely won't forget to clearly write down the unit as well. It is ampere, which is the standard international unit of electric current. So 0.45 amperes is the current passing through this circuit. In this way, you were able to get familiar with the concept of watt and also learn an equation and perform calculations accordingly. Now, here we have some concepts about power that will help us better understand certain ideas in the following sections and also help us grasp the concept of power itself more thoroughly. There is a concept, or rather a term, called loss. The term loss is often used in relation to power. Just as we said that energy can be transformed by a flow of energy into other forms like light, heat, sound, and so on. If we see these, it's useful for us because we can observe their tangible effects. In other words, we can see the action that this electric current has produced for us. But when it appears as heat and light, this energy is being carried by the electric current and is being converted into heat and light. We say that the circuit has lost power. For example, let's say that 100% of the electric current is flowing, and now suppose that 10% of it is being released as heat due to those processes and conversions. For example, consider incandescent bulbs. They feel warm, even hot when you touch them. The amount of heat they emit, yes, they give off light, but the heat they produce, and especially tungsten filament bulbs, are very hot. That heat they give off is a loss, meaning we have energy loss. We experience energy wastage. That's why LED bulbs were introduced, which, as we can see, produce less heat, meaning they waste less energy. In addition to providing us with light, they also waste less energy, making them more efficient. So the term loss that I mentioned here refers to power, and mostly to the energy wasted when we use electric current. Now, this issue also applies to other electrical devices. For example, imagine when we turn on a meat grinder, we see that it's working and giving off some heat. This amount of heat that it gives off while operating, that's what we call loss. Now, for example, if it's an electric heater with an element that gives off a lot of heat, its very purpose is to produce that amount of heat. But we need to keep in mind that it depends on its wattage, meaning the higher the wattage, the more heat it should produce, right? If it gives us less heat than what its wattage suggests, then obviously that heater isn't working properly. Now let's move on from this topic. This was about energy loss or wastage. One point to note here, which I also mentioned during the lesson, is that we represent current and voltage with certain letters like I and E. But in some books, for example, current is also represented by the letter C, or as we've seen, voltage is shown as V in books, and power is represented by the letter P. To help you focus better and have a general categorization, here I have created a table so you can more easily keep the abbreviations in mind and use them. We represent electric current with a capital I, and its unit is ampere, which we denote with a capital A. Voltage is represented by E or EMF, and its unit is volt. But generally, especially in textbooks, it is shown with a capital V. However, if you see it elsewhere, know that you can use it this way as well. Power is represented by a capital P, and its unit is watt, as you can see here. Alright, that's it for now, and this topic was related to watt. If you remember, I said that in order to understand voltage, you need to grasp another concept called power. I hope that up to this point you have understood the concept of power, which I will explain once more. Power is the work done by an electrical circuit, and its unit is called watt, which is defined as the amount of work done by a circuit that conducts 1 ampere of current with 1 volt. Alright, so up to this point, that's power. But as we said, in order to better understand voltage, it was necessary to first understand power. Now I can give you a simple definition for volt here, so listen carefully. It's a very short sentence. 1 volt is the amount of electromotive force required to do 1 watt of work at 1 ampere of current. So what does that mean? 1 volt is the amount of electromotive force. I refer you to the video about voltage, where we discussed electromotive force. electromotive force, which we represented with EMF. So 1 volt is the amount of electromotive force required to do 1 watt of work at 1 ampere of current. Now, there's another important point I need to mention, so let's go back a little bit. This particular equation here is often used as Joule's law, named after the distinguished person who discovered it. That was another point I wanted to mention to you. In conclusion, I can say that calculating the power lost by the circuit is often considered a very important part of circuit design. This is because electronic components like resistors, transistors, capacitors, and integrated circuits (ICs) all have a maximum power rating, and if more power than this is applied to them, they will definitely burn out. That's why we need to consider the required power in our circuit design, calculations, and the components we use, and take all these factors into account together so that our circuit works properly. Well, the topic of power ends here. In this section, we became familiar with the concept of power. We also learned its formula, how to use it, and saw that it depends on electric current and voltage. And in future sessions, we will be working more with these topics and making use of them. So until the next session, goodbye.